Good afternoon. I'm Larry McAdams from Cisco. I'm part of the 12,000 team. I'm going to talk to you about some emerging protection options for IP over optical transport. The issues of protection have traditionally been very coupled with SONET. So before I launch into the options that are coming now, I'm going to spend a couple of slides just talking about what's going on with SONET, what's going on with IP over SONET, and why the SONET topology is being stressed, and why it's maybe not the best thing to get the protection out of the SONET layer. And then move on to essentially the kind of options that are emerging in the vacuum around the SONET today, which is the optical protection mechanisms. Specifically, we're going to talk about mesh restoration and optical cross connects. And then also there is now 50 millisecond restoration in the IP plane through MPLS. So we'll talk a little bit about that. And then we'll try and bring the two back together and make some sense out of which one you should use, or what can we do to bring the two closer together. So before I get started into the issues with SONET, I wanted to begin by saying that very clearly which parts of SONET I'm referring to and which parts aren't. Because there's really two SONETs. I mean, it's one standard, but people use the term SONET to really mean what I think is fairly two distinct things. One is the SONET protocol and the framing, and the other is the SONET architecture. And it's the architecture portion that I think is under stress, and that's the part I'm going to talk about. The SONET protocol and the SONET framing is still very much alive and well in packet over SONET and other transport approaches. But saying that really brings about the point about why SONET is under pressure now, because SONET is the most wonderful transport mechanism you can think of to move voice around. It's really superbly architected for voice. It does a tremendous job of multiplexing little tiny skinny pipes up to big fat pipe. Well, in a TDM sense, well, that's not needed quite so much anymore now that we have stat muxing in data devices. So that's, at least in the core of the network for IP, has largely faded, the multiplexing function. But the one that remains is the fast protection that comes from SONET. However, as you'll see in the next couple of slides, with the changes in the paradigm for the core architectures around transport, there's a great interest in looking to see if that last remaining strong function of SONET, the self-healing 50 millisecond ring, can't be replaced with something in a different layer. So the story really begins by looking at typical North American backbone from a transport layer, from the SONET layer. And the first thing to recognize is that you don't just build one big ring around the country. You build the country out in a series of rings. This is done for a variety of reasons, ranging from the fact that SONET can't build a ring as big as this country. It has 1,200 kilometer diameter limit if you're going to be in spec. And also the fact that the carriers didn't choose to want to do that in many cases, because they wanted to be able to segment the network at the transport layer. So for instance, they could do maintenance on one ring without disturbing the other rings. However, the other part of the ring topology that's implicit in here is really that when SONET was developed, as I said before, it was really developed around voice, and voice falls off with distance. You're more likely to make a phone call to your friend within the town than you are make a phone call across the country. Now, that breaks down a little bit, but it is still quite true that it falls off with distance pretty strongly. And therefore, these SONET rings weren't so bad, because most connections weren't the one I showed you going from San Francisco to New York. Most collections were captured inside one ring, and so it wasn't a problem. But this is not the case with IP. IP tends to be distance independent. If you're outside the United States, you're as likely to be hitting another continent to get to your content as you are to be finding it inside your own town. And here in the United States, you're likely to be finding it on one of the two coasts. So you're going to go pretty far, is the point. And it's the fact that the paths now are coming as long as they are is one aspect of why the rings are breaking down. As we'll talk, this situation is one way of viewing it is the action of provisioning. I won't mention any names, but there's a well-known carrier who not too long ago made a press release saying how very, very proud they were that in a mere 6 weeks, record time, they were able to provision OC12 circuits across the country. 6 weeks to get 4 of them up. Well, in the world that we live in now and the changing networks, 6 weeks isn't fast. 6 weeks is not a good number. We're looking at provisioning systems, I think, in the next set of transport networks that will be able to do coast-to-coast provisioning in seconds. And you'll see why when we talk about the optical cross-connects. So the other part of the puzzle has to do not so much with SONET per se, but with the advent of WDM coming into SONET. Because remember, the first generations of WDM were essentially fat pipe expanders. They were meant to go into the SONET rings and to expand the virtual fibers that you had in your ring. So in traditional SONET rings, when you come between 2 rings, you exit one ring, you drop into a cross-connect system, and it cross-connects the time slot on the incoming ring to the time slot on the outgoing ring. When WDM came along, this problem became a lot worse because WDM very nicely solved the problem of giving you lots of capacity in the fiber. But in the early days, really what it did in SONET rings is allow you to build concurrent rings, concentric rings, namely that inside one fiber you can now have n virtual rings if you've got n lambdas in your WDM system. Each one of those lambdas is backed into an add-drop multiplexer. And so you have an add-drop multiplexer for every lambda you've got in your WDM system. And now comes the problem of wanting to interconnect between your rings. And the problem is frustrated greatly by WDM. It's not enough, like you see here in the picture, to have add-drop multiplexers for every wavelength, because to be fully connected, you need to be able to get from any lambda in any time slot across this interconnect over to the next ring on any lambda any time slot. And therefore, you cannot have stacked digital cross-connects to solve the problem. You have to have one massive big cross-connect to solve the problem. So we don't just have a linear problem here with capacity increasing. You know, if there's n wavelengths, you don't need an n-fold bigger cross-connect. You need an n-squared bigger cross-connect. This terribly frustrates the problem. And again, going back to provisioning, traditional systems have an element management system for that SONET ring, which has to be interacted by your fingers, generally, to set up a time slot in the first ring. You have to interact with the other ring. It might be another EMS. Then it's a separate system to go into the DCS and set up the circuit across those ADMs. It's very painful and has to be done at practically every central office. If you look at it from that point of view, 6 weeks to go across the country was pretty fast. But it's got to do with this problem in the CO and more than anything else. And rapid provisioning is certainly something both in the wide area and the metro area has become a hot topic. So, in comes the optical cross-connect. This has a number of profound changes. The simplest one is here, just to look now, we have the ability to step outside the rings. From the transport perspective, you don't have to capture your traffic into nice round rings anymore. It didn't really want to be nice and round in the first place, so why not have a more arbitrary topology? Well, they've known how to do this for a while. The problem is they didn't know how to make it go very fast. Particularly on the protection side, it became too complex. And the traditional models said, well, these cross-connects should send the messages up to an EMS that talks to an NMS that will think about it and send it back down the EMS and rebuild your configuration. Terribly slow, generally minutes historically. However, now we have a generation of cross-connects that is intelligent, as you'll see in the next slide, and we can do this in a much more efficient, manner. Now we have the ability to do it essentially real time. And what they're really aiming at is a couple of things. I'm going to concentrate on restoration, but just to list a couple of other ones that they're aiming at is by moving to a mesh network compared to a ring network, you can, generally speaking, recover something on the order of about 50% of your bandwidth because the rings always have 100% set aside or worse. So there's a great play on efficiency that you get from these rings, from the mesh topology that you didn't get from the rings. And the other thing is, if you want to be able to do traffic engineering in a more automated fashion, you can do that now. You can set paths up, you can point and click. But let's keep to the restoration track. Before we go into the restoration side and talk about this, it's the other important thing to understand about the optical cross connects is that they have intelligence. They are not the automated patch panels we had before. They're not jumbo Tel Labs products. These are a whole new generation of cross connect that is essentially meant to manage wavelengths connected to the WDM systems. And it does this by essentially having layer 3-like intelligence for the first time in layer 1. So they have reachability protocols, they flood link state databases to their neighbors, and each box has a real-time copy of the topology of the network in it. Just like a router, except it doesn't know about packets, it knows about fibers and wavelengths and circuits. And all this information is spread through the network, again, because they know about packets. They can't create packets. So they reuse the overhead in the SONET frames today. Typically in the DCC channel, they've got about 200 kilobits per second of bandwidth in DCC that they can use to communicate amongst themselves. So, what does it give you from a restoration perspective? Well, unlike SONET, which was essentially designed as the end-all and be-all of voice transport, and in such a case, SONET was designed to only have one kind of restoration, all or nothing, because it only carried one kind of traffic, voice. But today, we are in the process of building IP networks that support classes of service. There's a whole variety. You folks know them better than I. Here at the optical level, what's going on is they're creating different classes of restoration. So inside this mesh network, you could have, mission critical traffic. Mission critical traffic is protected in the fastest and first. Numbers today are 50 milliseconds or better type numbers in wide area networks using the optical cross connects. And really what they're doing is they are using their OSPF-like protocols to predetermine restoration paths and to pre-allocate, in some cases even, the bandwidth on the restoration path. So in a sense, it's kind of like the 100% set-aside that SONET had, but it's only for the traffic that you so desire. It's not all traffic now, it's only that which the customer pays for mission critical. Another example would be a premium class for internet where you've got rapid, probably 100 millisecond-ish kind of restoration numbers. You have predetermined what you're going to do if you have a failure, but you have not pre-allocated any bandwidth. So you're going to bump somebody, you're going to preempt somebody off their line to get back the bandwidth you need for restoration. And then there's also the public internet, which this class essentially says, well, if we've got a fast setup or a fast provisioning mechanism because we have link state information for the network, then restoration will just be try again. In this case, you go through another setup and you can get restored in the order of a second kind of number, broad terms. And then the final class is sort of best effort. Not even best effort, it's worse than best effort, because here in this class they say, well, we've created some restoration resources, a pool of restoration resources that the mesh can use as needed to restore links. Well, let's sell some of that restoration bandwidth to somebody. In other words, let's let people know that they can run over that, but be warned that you're in the restoration bandwidth, and therefore it doesn't matter if your line goes down. If potentially anybody in the network's line goes down, and that person has a higher priority than you do, they're going to bump you off your bandwidth because you're at risk. You're on the restoration bandwidth. So the point is, you can create this whole spectrum of options. They exist here in restoration, but there's other like-minded things. You can talk about delay, have different classes of delay performance. The point is, with a mesh restoration mechanism, you've got a lot more freedom than you ever had before. Okay, so I'm going to switch a little bit. I'm not going to say too much about MPLS to this crowd. I just say that the parts that are relevant to the discussion we're going to enter into here, which is that now if we look at wanting to do fast restoration at the IP level, what it really comes down to is you need to have a notion of connection, which isn't too common in IP. However, fortunately, MPLS has that. So MPLS, the notion of the tunnels can be used as a connection that can be controlled for restoration purposes. The other big deal I think you'll see as we start to unfold this is that because MPLS operates on packets in cells and knows about connections, so it can be extended to work on circuits and lambdas, we have the opportunity here to create a unified control plane. And in fact, you'll see the IETF is working quite hard on that very direction. And the unified control plane is very important from the point of view of saving cost on operations. As you may know today, you generally have different departments that keep track of different layers that have meetings to talk about how they're going to coordinate their layers. Well, if you have a unified control plane, you don't have to have so many departments because one department has visibility into all layers of the network. So there is something coming out known as fast reroute technology in the MPLS plane. It's got two parts to it. It's got a link or node protection part, which we'll talk about here, and then it's got a path part that we'll talk about in the next slide. So the point here is that you, through the labels, by pushing a new label on, if we have a broken link, I've shown it as a router because actually the notion is that for every 2 links in a router, you put you configure another path around. So whether it's a link or whether it's a router now, it doesn't matter because you can get protected in 50 milliseconds in both cases. Again, an example of where you didn't get it from Sonnet, but you can get the node protection natively now in this technology. So when either the node or the link goes down, using Sonnet overhead, we can detect at the near end, shown on the left-hand side of the slide, that we have lost the link. And what we do is we push on a new label onto all the tunnels today traveling that link. In the future, we'll be able to color the tunnels and say, well, is this a restorable tunnel or not? But today, we push on a new label and send it up the north path there over the extra hop through the 2 routers and back down. Pop the label off, and off we go, and nobody knows the difference. It's a local action. And the nice thing is we've been doing some work, and it looks as if it's pretty darn scalable. Certainly today it's very easy because we're not coloring the tunnels, and so we just take every single tunnel as if we don't care what it is and pop a new label on top of it and route it over the northbound. And the early results that I'm aware of have shown that thousands of individual tunnels can be rerouted in well under the 50 millisecond number. It's an extremely fast process. And I believe it's scalable because the tunnels already have a certain level of aggregation. So ultimately, there's not a huge number of these tunnels, and they're going to be colored, so you're really going to have groups of tunnels with similar attributes. Then the final point is, as I mentioned, this is entirely a local event as we've talked about it so far. Only the head-end router on the left-hand side is involved in this. The rest of the folks really don't know what even goes on. However, now I'm going to change the slide, and before I do, I want you to look at this picture one last time, because now I'm going to talk about the path protection, the re-optimization that goes on across the entire network. And the starting point to that is to say that this head-end router that's responsible for pushing the new label on for the local repair also sends an RSVP message up to the head end of the tunnels. And with that, we can do more. So there's a second part, and I chose the words purposely. The 50 millisecond protection is a local action. Now we're talking about path restoration. We did not lose any traffic after we did restoration, after we did protection. So as of the last slide, we went around the failed router or the failed link, and all the traffic is back up and flowing. Now the question becomes, do you want to re-optimize from the head end? Because you may be on a suboptimal path. So the RSVP message flows up to the head end of the tunnels, and then which alerts them that there's been a protection event and they should look for new topology information. And then either through an IGP update or through explicit signaling through RSVP, the head end of the tunnel may select to re-optimize its path. And this whole process, right now, depending on your IGP and whatnot, is on the order of seconds. Can be very low number of seconds, but it can be tens of seconds too, depending on your IGP. There's no traffic loss though. During the protection event on the previous slide, we got the traffic flowing. Now it's just a question of, in the background, re-optimizing paths. So that, in a very brief way, is the two approaches that are emerging. Both approaches are real-time, 50 milliseconds. Both approaches appear to be quite scalable, suitable for core. Both approaches are very efficient. Different people can see different views. You could say that the tunnels have slightly finer granularity. So you could say maybe the tunnels are a little bit more efficient, but both of them are pretty close. The big difference is one of them's operating on a circuit, generally an OC48 level circuit, if it's the optical cross connect, whereas the MPLS folks are operating on the tunnels. There could be several tunnels in the circuit. So how do you choose? Because either one will work, either one will get you there. So I think the simplest high-level answer there is it depends on the services you're running. If you are a provider of layer 1 circuits, then it probably makes sense for you to think about layer 1 protection through the optical cross connects. However, if your business model is to offer layer 3 services, then the MPLS might be the best solution for you. You get a little bit greater, a little bit finer granularity, and you probably already have a lot of routers running in the network in that case anyway, so you're well prepared. Well, you could look at it a couple of ways. You could ask yourself, well, maybe it's a divide and conquer in that case. And I would say, no, don't let it be a divide and conquer, because if you divide, you'll get conquered. Each of these have a little different view of the network, and we need to bring the views together. The network really is one big entity. I mean, you can't tell where it broke. All you can tell is it's not working, the user. At the optical level, the intelligence at L1 essentially gives you the visibility into the capacities of the network. In other words, the state of the links and the unused lambdas and fibers that are available. Layer 3 has intelligence, but it really knows about reachability of the links that are up. These are somewhat distinct, and we'd like to capture both of them to get the best of everything. So, one way that this may go forward is there is some activities going on at both the IETF and now the OIF on multi-protocol lambda switching. Basically, the notion is that there's emerging a number of proprietary technologies in the layer 1 intelligent optical devices. This intelligence looks a lot like a layer 3 protocol, so why not think about unifying them? Why not think about letting even the customer choose whether they want the routers to appear as an overlay to the optical network or whether they want it to appear as a peer to the optical network? With MPLS, you can get that choice. You can have a spectrum and the customer can choose what they want. And what would you get if you did have that kind of visibility across both the optical and the routed layers. Well, the routers could now make much better path selection. They don't just know about who they're connected to and who their neighbors are connected to. They know about who they could be connected to. They know about alternative routes that may not be in place yet if they had knowledge from the capacity side of the optical network. It simplifies provisioning. With a single control plane now, you can provision circuits and packets seamlessly, not only in the wide area, but think about this in the metro area too. We call it multi-protocol lambda switching, but there's nothing unique about a lambda. It's fundamentally a circuit. And you could be operating at channelized circuits as well. So you could, for instance, in a metro area, imagine plugging a channelized interface on a router into a SONET device that has STS1 granularity in its cross connects. And seamlessly, you could configure the IP sub-interfaces and the STS circuits in one action through one control plane in a metro area. So it's not just wide area, it's also about the metro. And then finally, it's money. Operations is a significant part of most service providers' networks. Lowering the operational complexity lowers the amount of work that has to be done by the operations team, and that saves money. At the end, I've just shown there is a couple of drafts out at the IETF now. This one I've shown here from Daniel Aducci at UUNet is essentially the high level. It's the first multi-protocol lambda switching draft that describes the motivation from a carrier's perspective on why this makes good sense. That's all I had for you. I'd be happy to entertain any questions. Thank you. Oh, good. Yes, Ross.
Hey, Larry. Could you comment on whether you can really get carrier-grade restoration if you're sending the far-end remote failure information at layer 3 in an RSVP? Do you still think you can get the carrier-grade restoration capability at MPLS?
We certainly do.
You don't think it's a bit flaky doing it at layer 3, no?
No, I think the chance that your packet's going to get through is about as good as if you put the command in the DCC channel.
Yeah, but you can't get the guarantee that you could get with like a K1, K2 byte in a SONET. No?
Well, the K1, K2 issue is essentially analogous to the local link and node repair, and there we're using the same SONET signals that we're not using K1, K2, but we're using the SONET overhead signals that are carrier class, to use your words.
At the receiver end, but the far end remote failure, I thought you were doing that with RSVP, you know?
Well, when we signal up to the head end of the tunnel, yes, we're going to send an RSVP message.
Right. Thanks.
I think what he may have been trying to get at was a current deficiency in the implementations of OSPF, where reverse sense of unidirectional failures is not handled properly, where a receiving side seeing a link failure is treated as if it's the sending side that has failed.
Yeah, I mean, before it goes into prime time, there's a few of those little nits that are going to get worked out, but I don't see them as fundamental showstoppers in any way.
Is there going to be only at the multi-protocol level, or are there going to be extensions to OSPF for?
Yeah, there are. In fact, there's a third internet draft that's being produced this month, and will probably go up this month as well, that essentially outlines the extensions to MPLS, ISIS, OSPF, and RSVP. So the good news is, and I'm very glad you asked the question, because people say, well, how much work have we got to do to make this extensions work? And the good news is that is a complete list of the extensions, best it's known today, and it's 4 pages long. So we think that we'll have an internet draft that people can begin to implement on in early, maybe March.
Hi, yeah. Your talk pretty much talked about wide area networks and meshes versus rings, that sort of thing, but toward the end of the talk you said something that these same ideas they make sense for the metro area where you don't have a mesh. Typically, I guess you'd have a ring. Could you comment on on that? Explain that to us.
I just kind of threw that in as a little caveat, but imagine a metro ring, and you have a number of customers that want to be provisioned as point-to-point circuits through the time slots on the ring. And these circuits are going to be used to connect data devices together. So today, you would send somebody down into your SONET system to figure out where those time slots are and assign them to the two endpoints of interest to bring up a circuit. You would then plug your router in and start typing away to configure your IP interfaces. It's a two-step process. It's going to be done by two different kinds of craftspeople, probably hours at least apart from each other. The notion is that since you can control circuits with lambda switching as well as lambdas, why not push the MPLS control plane into the metro areas as well, onto the metro rings in this particular example, and then you could sit in one place and configure your router interfaces and your STS circuits and time slots as one single action.
Please take this as a serious question rather than as a cheap jibe. Right back in slide 3, you said the one of the drivers to give optical protection on this stuff was getting high availability and low cutover time. If you're driving for multi-nines availability, the main problem that we have at the moment is not quick cutover, it's nodal availability. And I sometimes wish that vendors would spend more time increasing nodal availability by having code that didn't crash all the time, rather than adding additional features, which seems to decrease this. It's all very well saying you have 50 milliseconds cutover in event of a fiber break. If my 12,000 takes a minute to reload, this doesn't help me.
Well, it's a separate talk, but there's something called ENA. And then the other is the cross connects. The cross connects were built by the transmission people like battleships. So if you view your network through the optical cross connects, you probably find they have somewhat higher availability. Okay, thanks again.
Thanks, Larry.